Oh, clean up, everybody, everywhere. Okay, so what we're going to talk about here are Rlc circuits. This is a next step off of the simple harmonic motion video that you hopefully just watched as a flashback, or maybe you just saw it as the first time for your mechanics course. But what we saw in that video was mass spring oscillators, bouncing back and forth, left, right, or up, down, and pendulums, rocking like this. We're going to use those same ideas of harmonic oscillations, but for Rlc circuits, circuits that just have inductors, L, and capacitors, C. So what we have here are 4 different stages here of a Rlc circuit. Let's look at stage 1. What we have here is we've just charged a capacitor to full. So we've got a positively charged capacitor here, and the current hasn't flowed yet. Okay. The current is going to flow for this capacitor, eventually down like this, because we're going positive and negative for conventional currents. And that means that sometime later, whenever we get over to our second position 2, we're going to have a maximum current flowing through our system. Well, when this current is flowing, it's going to create a B field in this inductor, because that inductor has loops, and as the current passes through the loops, that current has a B field on it, and the B field goes through the loops. And when that occurs, a B field will also be induced in that inductor in order to generate a opposite current. So that B field is going to be induced here, and in doing so, that induced B field is going to give us a changing flux, which will allow us to have an induced EMF and an induced current. Okay. Sometimes later, though, whatever that is, our charges are going to go around such that the bottom side of the capacitor will now be charged positively, and the top will be our negative side. And when that occurs, we're just going to get a cycle again. We're going to get currents running around, and in doing so, well, we've got this here, and in doing so, the currents are going to begin to run around at some maximum. And when they do that, we're going to get the same kind of B field effects, induced B field, and then we're going to get a induced current out of this. And when that happens, we're going to get back to this initial phase here. So we're kind of going around in a big loop here, over and over and over and over and over again, which is exactly what the back and forth, back and forth, back and forth of the mass spring system did. Now, if we compare this to a mass spring system, well, initially, what we have in stage 1, whenever we're getting ready to go, this is like a fully stretched spring. Okay, so I've got some spring. This line here is the equilibrium position. I stretch it out beyond it, and then I'm about to let go, blue, and then I let go, and I start it. Sometime later, we get to a maximum current. Well, that's like your mass has reached the equilibrium position, and when it gets there, we know that we are at our max speed at this point. We're moving our fastest. Okay, we're moving in this way, but we're moving our fastest. Later, we get to world 3 here. We've reset our system. We're at a full compression for our spring. So it's stopped for a moment, but it's getting ready. It's like reset. And then bang, it opens up. It's moving to the right again at a max speed sometime later. And it'll just keep doing this over and over and over and over and over again ad nauseum, assuming that there's no friction for the mass spring. And for our circuit, what that means is there's no resistance. So there's no resistors. The wires that we have are perfect conductors. They're like superconductors. And it will do this just forever and ever and ever. We don't actually have perfect systems in the real world. We actually generate what are known as Rlc circuits, but that's a little bit beyond the AP Physics C, E, and M content. We'll talk about it in a future video, though, because you'll need it in college. Okay, but this is just going to go back and forth over and over and over again forever. So let's talk about what that would look like on a mathematical standpoint. We know from the SHM video, we want an equation that reads x double dot equals negative omega squared x, where this x is really some function x of t, and this x double dot is the second time derivative of that function with respect to time. Okay, so it's that second derivative of the initial function with respect to time. This is what we want, though. Okay, if we can get an equation like that, we'll be all set for our Rlc circuit system. Well, let's do this. I knew from just talking about this in our last SHM video, that a sine or a cosine equation works well. So let's set up that the amount of charge on our capacitor as a function of time, let's say that equals big Q, which is like the total possible charge the capacitor could ever have, multiplied by the cosine omega t plus phi. And if you watch the old video, you know this cosine omega t phi term is going to come up because when we take two derivatives, we're going to get it back. So let's actually take two derivatives here. We can say that Q dot, which some people like to write this as the first time derivative of Q, which also we could write it as the current. Ooh, that's pretty cool. We'll see why we need that later. This is just equal to, and if we take the derivative here, negative omega Q sine of omega t plus phi. And if we took the derivative once again to get Q double dot, or the second derivative of Q with respect to time, which we could also write as just the first derivative of the current, this is going to equal negative omega squared Q cosine omega t plus phi. And this is perfect for us because we know that Q cosine omega t plus phi, that is equal to just Q. That's what we had up here, right? So I can use this equation as a simple harmonic oscillator, looking at the amount of charge stored on the capacitor. Now, how would we go about doing that? Well, let's think about this. Let's go to our Kirchhoff loop real quick. So here's our capacitor, and here's our inductor. Let's walk around the Kirchhoff loop and see what we get. If we go around the Kirchhoff loop, remember, we're looking for changes of voltage as we walk around things. When we walk around the Kirchhoff loop, the change of voltage for the capacitor is whatever charge is on that capacitor divided by the capacitance. Okay? Sometimes this is big Q if it's fully charged, but if it's not, it's just little q. So if we're going across our capacitor and we're gaining that EMF or that voltage, we can say that, hey, we've got some Q over C. And then if we're going across the inductor and we're losing all of that, so minus, we know the voltage across an inductor is L di dt. So minus L di dt. And we've completed the Kirchhoff loop, so that equals 0. Well, if we go back into what is di dt, what is this? We actually know what this is. If we take a look at what is di dt is just this idea of the Q double dot. Okay? And furthermore, it's actually, the derivative of this current, and we know this current is a negative, we get a negative quantity out of it. So what we can kind of say here in looking at this is that since our current can be thought of as, in our case here, a negative changing of the charge with respect to time, when we go ahead and rewrite this as the second derivative here, we're going to have Q of C, and then we're actually going to get two minuses here. We're going to get a negative that pops in on this di dt, which will actually turn this into a positive value, okay? We see this as, well, let's get rid of the L, because we don't need that. We see that because we can say di dt is equal to this idea of the derivative with respect to time of negative dq dt. It's the amount of charge we are losing in this system, okay, or in this capacitor as it's moving through. So if we do this, we get an extra negative here. The negative of my negative is my positive, so plus L, and then di dt, we could just write that as Q double dot, which will equal 0, okay? So the important thing here is be careful about this positive sign. We want to say negative here, but there is a extra negative that kind of pops up through in here. So this is, in green, that's our Kirchhoff loop. Now if we go ahead and solve this Kirchhoff loop, to set it up to look similar to x double dot equals negative omega squared x, How would we do that? Well, let's move the Q over C to the other side. So I get LQ double dot equals negative, and I'm going to write this as 1 over C times Q. And then if I divide each side by L, what we'll quickly find is that Q double dot, the second derivative with respect to time of the charge, equals negative 1 over LC times Q. And this is exactly what we want. We have our X double dot, it's Q double dot, because we're looking at charges. We've got our X, it's just Q, it's charge as a function of time. We've got our negative, and we have our omega squared, which means that in our case, omega is just going to be the square root of that, square root of 1 over LC. Okay, and this is very nice because once we have omega, that's our angular frequency. We can equate it to a linear frequency, which we could use for all sorts of things to find the period of oscillation of going back and forth on these type of problems here. If you're setting this up, if you accidentally went through the Kirchhoff loop and, let's say you forgot, to make that positive and you left it negative, what you'd find at the end is that this would just be positive, and you'd be like, let's make it negative. I missed a negative somewhere, okay? Classic little physics trick. If you accidentally get this as a positive, you already know that you need it to be a negative, so just put the negative in. You just missed a negative somewhere, you're fine, it's still gonna work out in the end for you. But really, you shouldn't be forgetting that right there, okay? So that gives you exactly what the harmonic oscillation is going to be for an LC circuit. Now, why is this also so important? Well, it's because as this is going back and forth and oscillating, we can actually find the stored energy as a function of time. If you recall, we talked about the stored energy in an electric field and the stored energy in the magnetic field for an inductor. In this case, if you recall, this was Q squared over 2C for an E field, and for the B field, it was Li squared over 2. Well, this Q isn't just a static amount of charge. It is actually a charge that is changing. It is Q of T, which means that I can go back up and I can use this equation as Q of T. I can also, for I, use this equation. So if I go down here and I plug those equations in for Q of T and for I, and this is technically not just I because that current is changing, it's I of T, I'll get the following. I'll get Q squared over 2C times cosine squared of omega T plus phi, and for my B field, I'm going to get Q squared over 2C times the sine squared of omega T plus phi. And what this will really represent for us is essentially we're going to have the same peak for both of these. They're going to have the same amplitude, this Q squared over 2C. So let's just put that point up here. This is, Q squared over 2C. But they're going to oscillate differently. One of them will start at 0 and then, go the up, down, up, down. The other one will start up top and just oscillate in the opposite direction. So boom, boom, boom. Okay. So maybe this is the E field here, and this is the energy stored in the B field. But they are oscillating opposite of one another, which is a kind of interesting thing. And they're oscillating just due to the cosine and sine term. One other note: notice how I didn't make these values negative. I didn't make these values negative because cosine and sine here are squared. So whenever you get your value out, let's say it was negative, you're going to square it, and it's going to kick up to positive, which is kind of a neat thing about that. Okay. So we really don't see these equations too often, but it is important to recognize that the energy stored in the E field and B fields of the inductor for an LC circuit are indeed changing with time. And we got all of that by understanding simple harmonic motion, understanding the equations we wanted to build, and then using Kirchhoff's law to take us through that. Okay, so anytime we see RC circuits, RL circuits, LC circuits, go to your Kirchhoff loops, go to your Kirchhoffs, and set those up properly, and then use those to work through the equations that you want to get there. Okay? In our next video, we are going to talk about the last bit here. You won't need it for the APC exam, but in college you will. We're going to talk about Rlc circuits, what happens with resistors, inductors, and capacitors all in the circuits together. Because in order to get the simple harmonic motion here that lasts forever, we needed no friction, we needed no resistance here. What happens if we do include a resistance or some frictional variable here? How will that change things as we go along? Okay, but that'll be our next video. You don't need it, so if you wanted to say adios, you could, but we're going to do it anyways. But for right now, we are finished. So adios, take it easy, have a good one.